A very good morning, students. Myself, Professor Akshata Patil from the Department of Mathematics, PLS V80 Halia. I am handling third semester ECB and CSC branch. Our subject is Transform Calculus, Fourier series and Numerical Techniques. Subject code is 18MAT31. So in earlier session, we have discussed Taylor series method, and I have solved some examples based on Taylor series method, and I have given introduction to numerical method 2, that is modified Euler's method. Okay, so in today's class we are going to solve examples based on modified Euler's method. So the course learning objectives to familiarize with the importance of numerical techniques by solving various numerical methods, and the course outcomes are the students will be able to understand how to solve the ordinary differential equations by using numerical methods, and the Bloom's levels are L1 and L2. Now let us solve examples by using modified Euler's method. So that is numerical technique 2. Okay. Now example number 1. So previous session I have solved one example. So let us continue the examples based on modified Euler's only. So here example number 1. Using modified Euler's method, find y of 0.1 correct to 4 decimal places, solving the equation dy by dx which is equals to x minus y square, y of 0 which is equals to 1, taking h equals to 0.1. So in this particular example, they have given differential equation, is it? Dy by dx equals to x minus y square they have given. With the initial condition y of 0 equals to 1, means x naught is 0 here, y naught is 1, and they have given step size length h also, that is 0.1. They are asking to calculate y value at x equals to 0.1. Okay, now let us solve this example. So in solution, let us write by the data x naught value is 0, y naught is 1, and h is 0.1. Okay, so first we need to calculate f of x naught comma y naught, means by using the given differential equation to calculate f of x naught comma y naught. So let us write f of x naught comma y naught which is equals to, given differential equation is what? X minus y square. X means x naught value is 0 here. Okay, y means y naught value is 1. So 0 minus 1 the square means we will get the function of x naught comma y naught value is minus 1. Okay, now next we need to calculate y1 value by using the Euler's formula. Okay, so Euler's formula we already know. So formula is y1 of initial approximation, that is y1 of 0 which is equals to y naught plus h into the function of x naught comma y naught. Okay, so in this formula we know the value of y naught, that is 1, h we already know, that value is 0.1, and function of x naught comma y naught we already calculated above, so we'll get here minus 1, is it right? So substitute all these values and calculate initial approximation value of y1. So here we can write y1 of initial approximation which is equals to y naught is 1 plus h is 0.1, and function of x naught comma y naught value is minus 1, substitute, and after simplification we will get here y1 of initial approximation value is 0.9. Okay, now after this initial approximation, this accuracy is poor in this particular formula. We need to improve this accuracy to desired degree of accuracy by using modified Euler's formula. So first, right, take it first approximation here. So formula is y1 of first approximation which is equals to y naught plus h by 2 into the function of x naught comma y naught plus function of x1 comma y1 of initial approximation. So in each approximation, keep it in mind, you should use the preceding value of y1. Okay, so here we should use, in this first approximation we use the Euler's value, that is Euler's formula value. It means y1 of initial approximation value we should mention here. Okay, so put the values here. Y naught is 1, okay, plus h means 0.1 divided by 2. So open the bracket, function of x naught comma y naught we already calculated above, so that value is -1. So throughout this example, the function of x naught comma y naught value remains same only. Okay, so plus of function of x1 comma y1 of initial approximation. So once again put x1 and y1 of initial approximation value in given differential equation. Okay, so given differential equation is x minus y square. It means x is considered as x1 minus y is considered as y1 of initial approximation, the square. Okay, so here we'll get x1 means 0.1 minus y1 of initial approximation value, that is 0.9 the whole square. So simplified, you will get 1 plus 0.05 minus 0.9 minus 0.9 the square. So you will get y1 of first approximation value is 0.9147. So this is our first approximation value. Okay, so like that calculate second approximation here. So using the again formula here, that is formula is y naught plus h by 2 into f of x naught comma y naught plus f of x1 comma y1 of first approximation, means preceding value of y1. So here we'll know the value of y naught, that is 1 plus h by 2. H means 0.1 by 2 is 0.05 into bracket f of x naught comma y naught value we already know, that is -1. Okay, and plus x1 means it is also fixed throughout this example, so that value is 0.1. So -1 plus 0.1, it becomes minus 0.9 minus of y1 of first approximation value. So y1 of first approximation value means, write it down here, that is minus into 0.9145 the square. Okay, so you simplify it, you will get here 0.9132 is our second approximation value. Okay, now just check the first approximation value and second approximation value will be the same. Yes, both are identical to 2 decimal places. Here we'll get 0.91, here also we'll get 0.91, but here we'll get 9145, here 9132, means both the values of y1 are identical up to 2 decimal places. Okay, so let us calculate one more approximation here. So third iteration, or we call it as third approximation. So y1 of third approximation, once again use the above formula, y naught plus h by 2 into the function of x naught comma y naught plus function of x1 comma y1 of second approximation. Okay, so second approximation means, so the rest of the portion will be the same. Y naught value is 1 plus h by 2, it means 0.05, and f of x naught comma y naught plus x1, that value will be the same, minus 0.9 minus of y1 of second approximation, means preceding value of y1, how much you are getting, 0.9132. Let's square. Okay, so you will get here y1 of third approximation value is 0.9133. Okay, so just check the preceding value of y1 and succeeding value of y1, means second approximation and third approximation, is it identical? Yes, both are identical up to 4 decimal places. Thus, the y of 0.1, which is equals to 0.9133, is the approximate solution of given differential equation by using modified Euler's method. Okay, I hope you understand this example. Now let us take another example here. Example number 2, using modified Euler's method to solve the equation dy by dx, which is equals to 1 divided by x plus y of 0, which is equals to 1 in step length of 0.5 at x equals to 0.5. Okay, now in this particular example, they have given differential equation dy by dx equals to 1 divided by x plus y, and they have given initial condition y of 0 equals to 1. It means x naught value is 0, y naught is 1 here. Okay, and step size length h they have given 0.5, and they're asking to calculate y value at x equals to 0.5 only. Okay, now in the solution here, x naught is 0, y naught is 1, and h is 0.5. Okay, now first let us calculate f of x naught comma y naught. So f of x comma y is what? The given differential equation, that is 1 divided by x plus y. Okay, f of x naught comma y naught means x is considered as x0, y is considered as y0 in this given differential equation. So you will get 1 divided by x0 means 0 plus y0 is 1. So 1 divided by 0 plus 1 is 1 only. So f of the function of x0 comma y0 value is 1. So after calculating this f of x0 comma y0, let us apply Euler's formula. Okay. So Euler's formula is y1 of initial approximation, which is equals to y0 plus h into the function of x0 comma y0. So we can write it here. Y0 value is 1 plus h is 0.5. Okay, f of x0 comma y0 we already calculated above, that value is 1 here. So simplified we will get 1 plus 0.5 into 1, that is 0.5. So 1 plus 0.5 is 1.5. So y1 of initial approximation value is 1.5 here. So this value accuracy is very poor in this formula, so which we need to improve to desired degree of accuracy by using modified Euler's formula. So let us apply, or let us use modified Euler's formula. So first approximation. So write it down. First y1 of first approximation formula is y0 plus h by 2 into function of x0 comma y0 plus function of x1 comma y1 of initial approximation. So we know the value of y0, h value, and function of x0 comma y0 value also. So substitute all values here. So y0 is 1 plus h is 0.5 by 2, and f of x0 comma y0 we already calculated above. So write it down 1 plus f of x1 comma y1 of initial approximation, means once again use the given differential equation, and x is considered as x1, y is considered as y1 of initial approximation, and substitute the values here. So 1 divided by x1 means 0.5 plus y1 of initial approximation, means we already obtained the value of initial by using the Euler's formula here. Y1 of initial approximation value will get it here 1.5. So use the value in first approximation of modified Euler's method. Okay, so x1 is 0.5 plus y1 of initial approximation is 1.5. So simplified you will get 1 plus 0.25 into 1 plus 0.5. So we'll get y1 of first approximation is 1.375. Okay, now let us move to calculate second approximation. So formula is y0 plus h by 2 into function of x0 comma y0 plus function of x1 comma y1 of first approximation, means in this formula use the preceding value of y1. Okay, now y0 is 1 plus h is 0.5 divided by 2 into function of x0 comma y0, means we already calculated above. Simply put it the value here, that is 1 plus function of x1 comma y1. Once again use the given differential equation, so which is in the form 1 divided by x plus y. So x means consider as x1, here y is considered as y1 of first approximation value. So x1 means 0.5 plus y1 of first approximation value will get above here, so that value is 1.375. so substitute here and simplify it, you will get y1 of second approximation value is 1.3833. okay, now just check first approximation value and second approximation value. First approximation value is 1.375 and second approximation value is 1.3833. both are only for one decimal places, they are both are identical, is it right? But I need minimum 3 to 4 decimal places should match in both the approximations, is it? So let us do one more approximation here. So y1 of third approximation, which is equals to y0 plus h by 2 into the function of x0 comma y0 plus the function of x1 comma y1 of second approximation. So y0 value is 1 plus h is 0.5 divided by 2. F of x0 comma y0 we already calculated above, that value is 1. So plus f of x1 comma y1 of second approximation, means again once again introduce the given differential equation here, which is in the form 1 divided by x plus 1. So here x is considered as x1, y is considered as y1 of second approximation. So we'll get 1 divided by 0.5 plus y1 of second approximation value is 1.3833. Simplified, you will get y1 of third approximation value is 1.3827. Okay, now just check the second approximation value and third approximation value. Will you the both approximation values are same? Yes, both values of y1 are same up to 3 decimal places. Is it right? So if you want, you can do one more here for fourth approximation. Then also you will get the same value, that is 1.3828. Thus the y of 0.5, which is equals to 1.3828, is the required solution of given differential equation by using modified Euler's method. Okay, I hope you understand this example. Now let us solve one more example, that is using modified Euler's method to solve initial value problem dy by dx, which is equals to log of x plus y of 1 equals to 2 at the points x equals to 1.2 and taking h equals to 0.2. So in this particular example, given differential equation is log of x plus y. Initial conditions they have given x naught is 1, y naught value is 2. They are asking to calculate y at x equals to 1.2. And they have given step size length also, that is h equals to 0.2. Okay, some examples they have not mentioned this h value. That time we need to use the formula x1, which is equals to x naught plus h. Okay, so by using this formula we also calculate the h value. Okay, but in this particular example, h value they have given directly, so no need to calculate h value again. So let us solve this example solution. So let us write x naught value, that is 1, y naught is 2, and f of x naught comma y naught means the given differential equation, x is considered as x naught, y is considered as y naught. So function of x naught comma y naught, which is equals to log of x plus y. X means x naught, that value is 1, plus y is y naught, that value is 2. So 1 plus 2 is log of 3. So log of 3 value is 1.0986. So by using the calci, in calci you should press ln of 3, because here they have given log to the base e is there. Log to the base e means you should press in calci ln. Okay, suppose they have given to the base 10, that time you should press simple log in calci. Okay, so I hope you understand. I will get the log 3 value. Log 3 means press ln of 3, you will get 1.0986. Okay, now the function of x naught comma y naught value is 1.0986. Now after this one, let us use Euler's formula to calculate initial approximation value. So initial approximation value formula we already know, that is y1 of initial approximation, which is equals to y naught plus h into the function of x naught comma y naught. So we already know the value of y naught. Above they have given in the question only, y naught value is 2 and h is 0.2, and we already calculated above f of x naught comma y naught, that is log 3. Okay, so substitute all the values here. So y1 of initial approximation, which is equals to 2 plus h is 0.2 into f of x naught comma y naught means log of 3. So you will get 2 plus 0.2 into 1.0986. So you will get 2.21972 is the initial approximation value of y1. But here this accuracy is very poor in this formulae, which we need to improve to the desired degree of accuracy by using modified Euler's method. So let us do the iterations here. So first iteration, y1 of first iteration, which is equals to y naught plus h by 2 into function of x naught comma y naught plus function of x1 comma y1 of initial approximation. So put the value of y naught here, that is 2, h is 0.2 divided by 2 into f of x naught comma y naught. We already calculated above. So put it here, 1.0986 plus f of x1 comma y1 of initial approximation means, once again consider the given differential equation here, which is in the form log of x plus y. So x means consider as x1, y means y, consider as y1 of initial approximation. So log of 1 plus 2, 1.2 plus 2.21972. Okay, so simplified, you will get y1 of first approximation value is 2.2328. Okay, now let us calculate second approximation. So use the formula y0 plus h by 2 into function of x0 comma y0 plus function of x1 comma y1 of first iteration. Okay, so use the preceding value of y1 here. So let us write one more time y0 value, that is 2 plus h is 0.2 divided by 2 into function of x0 comma y0 value we already calculated above. So write it down here, 1.0986 plus log of x1 value. So f of x1 comma y1 of first iteration means once again use the given differential equation which is in the form log of x1 plus y1 of first iteration. So x1 means 1.2 plus y1 of first iteration means 2.2328. Now simplified, you will get y1 of second iteration which is equals to 2.2332. Now just check the first iteration value and second iteration value. Is it same? Yes, both values of y1 are same to 2 decimal places only. But in this modified Euler's method, we need to identical minimum 3 to 4 decimal places. Is it? So let us calculate third iteration here. So y1 of third iteration which is equals to, formula is y0 plus h by 2 into function of x0 comma y0 plus function of x1 comma y1 of second iteration. Okay, so put the value of y0 here, that is 2 plus h is 0.2 by 2. Function of x0 comma y0 we already calculated above. So throughout this example, this value f of x0 comma y0 will remain same only. Okay, so put the value here, 1.0986 plus function of x1 comma y1 of second iteration. Once again introduce here the given differential equation which is in the form log of x plus y, means x is considered as x1, y is considered as second approximation value of y1. So substitute the value here, x1 is 1.2 and y1 of second iteration means 2.332. Simplified, you will get y1 of third iteration value is 2.332. Okay, now just check second iteration value as well as third iteration value will be the same. Yes, both value are identical up to 4 decimal places. Thus, y of 1.2 which is equals to 2.2332 is the required solution of given differential equation by using modified Euler's method. I hope you understand this example. Now let us solve one more example here. So example number 6, applying modified Euler's method to solve dy by dx which is equals to x plus mod of root y of 0 equals to 1, compute y of 0.2 by taking h equals to 0.2. So in this particular example, they have given differential equation which is in the form x plus mod of root y. They have considered the initial conditions x0 and y0 value. x0 is 0 and y0 is 1. Okay, and h step size length they have given h, that is 0.2. They are asking to calculate y value at x equals to 0.2. So let us solve this example. In solution, dy by dx which is equals to function of x comma y. So that is nothing but x plus mod of root y. So here x is considered as x0 and y is considered as y0, and calculate f of x0 comma y0. Okay, so x0 we already know 0 and y0 value is 1 and h is 0.2. Okay, so let us calculate function of x0 comma y0. Substitute the value here, x0 is 0, y0 is 1. So equation is x0 plus mod of root y0. So x0 means 0 plus mod of root of 1. So you will get 1 only. Thus, the function of x0 comma y0 value is 1. So after this one, we need to calculate y1 of initial approximation value. So that is y1 of 0. So use the Euler's formula here. y1 of initial approximation which is equals to y0 plus h into the function of x0 comma y0. y0 value you already know 1, substitute here, and h is 0.2, and function of x0 comma y0 we already calculated above, substitute the value here, that is 1, and simplify it, you will get y1 of initial approximation value is 1.2. Okay, now this accuracy of initial approximation value of y1 is very poor in this example, in this formulae, which we need to improve to the desired degree of accuracy by using modified Euler's formulae. So let us take the formula here. So that is y1 of first approximation. y1 of first approximation, which is equals to, formula is y0 plus h by 2 into function of x0 comma y0 plus function of x1 comma y1 of initial approximation. Means use the initial approximation value in first approximation of modified Euler's method. So y0 value we already know, substitute here 1 plus h is 0.2 divided by 2 into function of x0 comma y0, that is 1, plus function of x1 comma y1 of initial approximation. Means once again use here differential equation, which is in the form x plus mod of root y. X means x1, y is considered as y1 of initial approximation value, and substitute the values here. So you will get 1 plus 0.2 divided by 2 into 1 plus 0.2 plus square root of 1.2. Simplified, you will get y1 of first iteration value is 1.2295. Okay. Now let us calculate second approximation. So formula is y0 plus h by 2 into function of x0 comma y0 plus function of x1 comma y1 of first iteration. Substitute the value of y0 and h here. y0 is 1 plus h value is 0.2 divided by 2. F of x0 comma y0 value is remains same throughout this example. So we already calculated above. So that value is 1 here. So 1 plus f of x1 comma y1 means once again introduce here the given differential equation, which is in the form x plus mod of root y. X means x1, y means y1 of first iteration value. So x1 is 0.2 plus y1 of first iteration value is 1.2295. So simplified, you will get 1.2309 is the second approximation value of y1. Now just check the first iteration value 1.2295 and second iteration value is 1.2309. They both are same? No. So let us calculate the third iteration here. So y0 plus h by 2 into the function of x0 comma y0 plus function of x1 comma y1 of second iteration. So y0 value is 1 plus h value is 0.2 divided by 2, that is 0.1 into function of x0 comma y0 value is 1 plus function of x1 comma y1 of second iteration. Means once again here introduce the given differential equation, so which is in the form 1 plus x plus mod of square root of y. So x means considered as x1, y is considered as y1 of second iteration value. So substitute the value of x1 here, that is 0.2, and y1 of second iteration value is 1.2309. Simplified, you will get 1.2309. So let us check second iteration value and third iteration value. They both are same. Yes, they both values are identical up to 4 decimal places. Thus, the value of y at x equals to 0.2, which is equals to 1.2309 is the required solution of given differential equation by using modified Euler's method. So students, let us So in this session, we have solved 4 examples based on modified Euler's method. I hope you understand how to solve the given differential equation by using modified Euler's method and how to get the approximate solutions. I hope you understand this numerical technique to modified Euler's method. So in last session, we already discussed numerical technique 1 Taylor series method also. So both methods are most important exam point of view. So let us practice these examples. So at the end of the session, students will understand what is modified Euler's method and how to solve the examples. In application, we'll see the modified Euler's method is one of the earliest analytic numeric algorithms for approximate solutions of initial value problems for ordinary differential equations. Currently, this algorithm is not applied frequently. These algorithms have several advantageous properties over the widely used classical methods. So here, students, I have given some video lecture links. Just go through these links. Try to solve the more examples based on modified Euler's method. Thank you for watching this video. Thank you.